Welcome to our universe. Right now, while you are still, Saturn is moving. It has been moving for 4.5 billion years without pause, pulling its rings in slow ancient circles, holding 83 moons in their orbits, drifting through cold so complete that hydrogen stops behaving like a gas long before it reaches the center. We are going to set Earth in its path. Not as catastrophe, as a way of understanding what both of these worlds genuinely are and what it takes to hold a planet together. If this feels like your kind of place, subscribe. Every person who finds their way here makes this universe a little more ours. Because this universe has always been large enough to hold questions like this one. Let's begin. Saturn has orbited the Sun 44 million times since the day it formed. Saturn is not a planet in the way Earth is a planet. That distinction is the foundation of everything that follows, and without it, the encounter between these two worlds does not make physical sense. Earth is rocky. It formed from the dense, metal-rich inner region of the early solar nebula, where temperatures were high enough to prevent lighter volatile elements from condensing into solid form. What accumulated instead were the heavy things: iron, nickel, silicon, magnesium, oxygen bound into silicate minerals. The result is a world with solid structure, from its surface through crust and mantle to iron core. You could pick up a piece of it. Its average density is 5.51 grams per cubic centimeter, denser than most metals encountered in everyday life. Saturn formed in a different part of the same system, beyond what planetary scientists call the frost line, the distance from the young sun where temperatures were low enough for water, ammonia, and methane to condense into ice. The outer solar nebula contained vast quantities of frozen volatile material alongside rock. The young Saturn accumulated a solid core of rock and ice. When that core reached somewhere between 10 and 20 Earth masses, something decisive happened. Its gravity became powerful enough to pull hydrogen and helium gas directly from the surrounding nebula. Not gradually, Saturn captured hydrogen by the octillions of tons and grew and kept growing until hydrogen and helium made up 96% of everything it was. The planet that resulted has no solid surface. This is not a simplification or a poetic shorthand for a surface that is simply difficult to reach. It is a physical fact with specific consequences. The cloud tops visible in photographs, those bands of amber, cream, and pale ochre, are made of ammonia ice crystals suspended in hydrogen gas at temperatures around minus 178 degrees Celsius. Below them, the pressure increases in an unbroken gradient. There is no boundary, no moment of transition from air to ground. There is only pressure rising, density rising, temperature rising, and hydrogen moving through states of matter for which ordinary language has no adequate words. At roughly 10,000 kilometers below the visible clouds, hydrogen passes through a supercritical state, beyond the thermodynamic threshold where the distinction between gas and liquid ceases to have meaning. The density and temperature have climbed so far that familiar phase categories no longer apply. Deeper still, at pressures exceeding 1,000,000 times Earth's sea level atmospheric pressure, hydrogen transitions into what physicists call metallic hydrogen. In this state, hydrogen atoms release their electrons entirely. Those free electrons move through the surrounding material the way electrons move through copper. Hydrogen becomes electrically conductive. It is this metallic hydrogen layer, driven by convection from Saturn's internal heat, that generates the planet's magnetic field. A field that extends nearly 1,000,000 kilometers in every direction, structuring the behavior of charged particles across a vast region of the outer solar system. At the very center, deeper than any probe has ever reached, there is almost certainly a core of dense material, rock, metal, and ice under conditions so extreme that the atoms behave differently than they do anywhere on Earth. Whether this core has a sharp boundary with the layers above it, or whether it grades gradually into the surrounding metallic hydrogen in what researchers call a fuzzy core, is not known with certainty. We infer it from the behavior of Saturn's gravitational field, from tiny irregularities in the planet's wobble, from the way seismic waves propagate through the interior and return altered. We have modeled it. We have not seen it. Saturn formed 4.5 billion years ago. Since then, it has completed approximately 44 million orbits of the Sun. It was already ancient when the first complex animal life appeared in Earth's oceans. It had completed the majority of those orbits before the first dinosaur walked. The number 44 million is too large to carry any intuitive weight, but it is simply the answer to the question of how many times Saturn has traveled around a star in the time available to it. That age sits in Saturn the way weight sits in iron. Quietly, without announcement, as a property of the thing itself. Earth fits inside Saturn 763 times. Numbers stated plainly. Saturn's diameter is roughly 9.5 times Earth's. Not 9.5 times larger in volume, 9.5 times wider in every direction. Volume grows faster than diameter. A sphere 9.5 times wider holds not 9.5 times the space, but something closer to 800 times the space. Saturn is not a perfect sphere. It spins once every 10.5 hours, fast enough that the equator bulges outward and the poles flatten. When that shape is accounted for, the real figure settles at approximately 763. Earth fits inside Saturn 763 times. Mass is different. Saturn is roughly 95 times more massive than Earth, not 763 times. The reason is density. Saturn's average density is lower than liquid water. If there were an ocean large enough to place Saturn in it, Saturn would float. Earth would not. Earth is one of the densest planets in the solar system. Saturn is one of the least dense objects of its size anywhere we've looked. This is the central fact that shapes everything else in this scenario. Earth is compact, rocky, iron-rich. Saturn is a vast column of compressed gas, mostly hydrogen, some helium, held together by its own gravity rather than by any solid structure. There is no ground inside Saturn. pressure increases with depth, and at some point deep enough, the hydrogen stops behaving like a gas and starts behaving like a metal. But there is no surface to hit. Saturn's gravity at the cloud tops is slightly stronger than Earth's at sea level, not dramatically, just slightly. They are the outer edge of something that extends inward for tens of thousands of kilometers without ever becoming solid. Earth arrives as a dense marble of iron and rock. Saturn receives it as a vast, cold, structured cloud. Before Earth reaches those clouds, something else happens first. Every large body has a zone around it where its tidal forces exceed the structural strength of an approaching object, where the gravitational difference between the near side and the far side of an incoming body is strong enough to pull that body apart. For Earth approaching Saturn, that boundary lies well above Saturn's visible atmosphere, roughly 12,000 kilometers above the cloud tops. Earth crosses that line before it reaches Saturn. The story begins there, not inside the atmosphere, above it. Something is growing in the eastern sky before anyone understands what it is. Begin with an evening in late summer. The light at that particular angle, golden, slanted, casting long shadows from ordinary objects across the ground. A familiar sky, pale blue darkening toward the east where evening comes first. Nothing unusual. The kind of evening that has happened on this surface billions of times before. As unremarkable as the rotation of her planet. Then something in the east is different. Not dramatically different at first. Different the way a feature of the familiar becomes unfamiliar. The way you look at something you have looked at 1,000 times and notice, without being able to say when it changed, that it has changed. There is a brightness in the east that does not belong to any star at that position. A point of light, white gold, brighter than Venus, bright enough on a dark night to cast a faint shadow across pale ground. Over days, it is visibly larger than a point. Over weeks, in binoculars, it resolves to a disk with an elongation to either side, a flat ring at an angle that shows the ring system as an ellipse. Over months, larger. Over more months, filling an increasing fraction of sky. The tides change before most other things do. The principle is straightforward. A distant massive object pulls more strongly on the near side of Earth than on the far side. The difference in gravitational pull across Earth's diameter creates a stretching effect. Earth's oceans respond to this differential, bulging toward the distant object on one side and away on the other, in the twice-daily rhythm of tides. Earth's moon, at 384,400 kilometers, creates open ocean tides of roughly half a meter. Saturn, at an approaching distance of 10 million kilometers, still far enough to appear as a large bright disk rather than a world filling the sky, would be generating tidal forces approximately 130 times stronger than the moon currently produces. The tides on the Saturn-facing hemisphere of Earth would be running several meters higher than any baseline in the recorded history of tide gauges. Coastal flooding events appear in the Saturn-facing hemisphere with no meteorological explanation. Waters rise at the wrong times, in the wrong directions, without storm or wind to drive them. At 5 million kilometers, Saturn spanning several degrees of arc, ring system visible to the naked eye as a complete oval stretched across a significant portion of the nighttime sky. Tidal forces produce ocean surface variations of tens of meters on the Saturn-facing side. The ocean is migrating, not rapidly, with the patient persistence of something driven by physics rather than by weather. The Pacific, the Atlantic, the Indian Ocean, all draining slowly and laterally toward the hemisphere facing Saturn, the water concentrating in a region of the planet that has no infrastructure to receive it and no geography capable of holding it. At 2 million kilometers, Saturn fills approximately 15 degrees of arc, 30 times the apparent diameter of the full moon. It is impossible not to see from anywhere on the surface. Its ring system, inclined at the angle determined by the approach geometry, catches sunlight differently from anything the sky has ever contained. The shadow of Saturn's disk on its own rings is visible as a curved darkness on the far side, a phenomenon that has no precedent in human visual experience. At 500,000 kilometers, Saturn and its rings together span a significant portion of the visible sky. The ambient light has shifted in color. The pale golden tan of Saturn's cloud tops, reflecting onto the landscape below, tinting the world a color it has never been. The ground is not still. Tidal flexing of the crust, the seismic response to gravitational stress, unprecedented in Earth's geological record, produces a continuous low-frequency tremor that no building in the history of human construction was designed to withstand. At 200,000 kilometers, closer to Saturn than Earth's moon is to Earth, the sky has become something for which no prior human language has a word. The eastern horizon is a planet. Everything that follows happens quickly. Saturn's gravity is already here. It has always been here. Gravity does not announce itself. It has no wavefront. It does not travel at the speed of light, or at any other speed in the way that light travels, carrying information from a source to a destination, departing from one place and arriving at another after an interval of transit. Gravity, understood through general relativity, is not a signal transmitted across a gap. It is a curvature in space-time, the shape of the geometry of space itself, modified by the presence of mass. Wherever Saturn is, the space-time around it has already been shaped by Saturn's mass. That shaping extends everywhere. There is no edge to Saturn's gravitational influence. Saturn's effect on the geometry of space-time reaches Earth's location right now, at a distance of roughly 1.2 billion kilometers. Its influence on Earth's path through space is real and continuous, simply overwhelmed by the Sun's far greater effect on the local geometry. As the separation between Earth and Saturn decreases in this scenario, the force that Saturn exerts on any given piece of Earth grows according to the inverse square law. Halve the distance, and the force quadruples. Halve it again, and it quadruples again. The growth is not linear. On a graph of force versus distance, the curve is nearly flat at large separations, and nearly vertical at small ones. There is a region of the approach where the rate of increase in tidal stress on Earth becomes rapid, and then there is a region where it becomes sudden. At a separation of approximately 200,000 kilometers, half the current Earth-Moon distance, Saturn's tidal differential across Earth's diameter exceeds anything in Earth's geological record. At this distance, we are still well above the Roche limit, which sits at 73,000 kilometers. But the effects on Earth's interior are already severe. The solid rock of Earth's mantle flexes under tidal stress. This might seem contradictory. Rock is rigid in ordinary experience. A hammer strikes rock, and the rock does not deform. But rock is only rigid on human timescales. Over the timescales of tidal cycles, and certainly over the weeks and months of an approach at the velocities involved, even silicate rock behaves as a viscous fluid. Io, the innermost large moon of Jupiter, is the most volcanically active body in the solar system, not because of unusual internal composition, but because Jupiter's tidal forces flex Io's interior continuously. The friction of that flexing produces enough heat to maintain hundreds of active volcanoes on a world 3,600 kilometers in diameter. Jupiter does not heat Io directly. It squeezes Io rhythmically from a distance, and the friction of that squeezing becomes fire. An Earth approaching Saturn would experience something analogous, though compressed into weeks rather than eons. The mantle would warm along the tidal axes. Convection patterns that have been stable for hundreds of millions of years would shift. The partially molten rock of the asthenosphere, just below the rigid lithosphere, would flow differently. Volcanic systems built on the dynamics of stable plate boundaries would lose that stability. New fracture zones would open along tidal stress lines. The seismic record of Earth's final weeks would be unlike any natural event in the planet's geological history. The magnetic field generated by convection in the liquid outer core would be affected as the differential tidal forces alter the core's fluid dynamics. Earth's magnetosphere, the field that has shielded the surface from high-energy solar particles for billions of years, would shift and distort, eventually failing as the core is disturbed. These effects arrive months before Earth crosses the Roche limit. The ground moves, not because the ground is unstable, because something enormous has been curving the space around it for 4.5 billion years, and it has finally gotten close enough for the curvature to be felt at the surface, in the body, in the rock beneath the feet of anything that still has feet. The moon leaves Earth before Earth reaches Saturn. Earth has a moon. In the collision scenario, this is not incidental detail. The moon is the largest object in Earth's gravitational domain, 7.342 times 10 to the 22 kilograms, orbiting at an average distance of 384,400 kilometers, taking 27.3 days to complete each circuit. It has maintained this orbit for approximately 4.5 billion years, since the debris of the giant impact that formed it cooled, coalesced, and settled into its current path. The relevant concept here is the Hill sphere, the region of space around a body within which that body's gravity dominates over the gravity of more massive, more distant objects. Earth's Hill sphere currently extends approximately 1.5 million kilometers from Earth's center. The Moon, at 384,400 kilometers, sits well within it. The Moon is bound to Earth, its orbit stable against the gravitational perturbations of the Sun and everything else in the solar system. As Earth approaches Saturn, Earth's Hill sphere changes size. The Hill sphere radius is not a fixed property of Earth's mass alone. It depends on the gravitational balance between Earth and whatever other massive body is nearby. The formula: the Hill sphere radius equals the Earth-Saturn separation multiplied by the cube root of Earth's mass divided by 3 times Saturn's mass. The mass ratio: Earth's mass divided by 3 times Saturn's mass equals 5.972 times 10 to the 24 kilograms divided by 1.705 times 10 to the 27 kilograms, which is approximately 0.0035. The cube root of 0.0035 is approximately 0.152. At any given Earth-Saturn separation, Earth's Hill sphere extends to 15.2% of that separation distance. When the Earth-Saturn separation falls to 384,400 kilometers divided by 0.152, approximately 2.53 million kilometers, Earth's Hill sphere has shrunk to exactly the Moon's orbital radius. The Moon sits at the boundary of Earth's gravitational dominance. Below this separation, Saturn's gravity at the Moon's location exceeds Earth's gravity at that distance. The Moon is no longer Earth's. The transition is not a sudden event. It is a gradual unbinding. As Earth's Hill sphere shrinks below the Moon's orbital radius, the Moon's orbit around Earth becomes eccentric. It wobbles, moves further from Earth in some parts of its orbit, closer in others. Over days to weeks, the orbit destabilizes. The Moon transitions into an independent trajectory determined by the combined gravitational field of Earth and Saturn, potentially entering a temporary orbit around Saturn, potentially escaping into a heliocentric orbit around the Sun, potentially being captured into Saturn's debris system as the collision proceeds. What the Moon does not do is stay with Earth. The Moon formed in the most violent event in Earth's history, a Mars-sized body striking the proto-Earth, vaporizing portions of both objects, the debris cloud cooling and coalescing into the satellite that has accompanied Earth through every geological era, every mass extinction, every configuration of continent and ocean, the entire span of complex life on this planet's surface. That formation happened when the solar system was approximately 60 million years old. The Moon drifts at a separation of 2.53 million kilometers. Earth continues alone toward whatever is next. Earth never actually reaches Saturn. The Roche limit. In 1848, a French mathematician named Edouard Roche published a calculation that established the distance from a massive body at which that body's tidal forces would exceed the self-gravity of a smaller body moving near it. His original formulation addressed fluid satellites. bodies held together primarily by their own gravity rather than by the tensile strength of solid material. The result was a threshold. Inside this distance, a fluid body disintegrates. Outside it, the body holds. For the Earth-Saturn system, treating Earth as a fluid body, which is the appropriate model for tidal timescales, because both rock and water flow under sustained gravitational stress given sufficient time, the Roche limit sits at approximately 73,000 kilometers from Saturn's center. Saturn's equatorial radius is 60,268 kilometers. The Roche limit for Earth lies approximately 12,730 kilometers above Saturn's visible cloud tops. Earth crosses this threshold before it enters Saturn's atmosphere. Earth does not collide with Saturn in the way that implies a surface impact. It disintegrates above Saturn. The distinction matters because it changes what the event actually is. The process of disintegration is not an explosion. It has no single moment of violent termination. It is the reversal of the gravitational accumulation that assembled Earth from the solar nebula 4.5 billion years ago, run backward in compressed time. Saturn's tidal differential, the difference in gravitational pull between the Saturn-facing side of Earth and the far side, exceeds Earth's own surface gravitational acceleration. Material on the near side effectively weighs less than it did. Then it weighs nothing. Then it weighs negative in the sense that matters. Saturn's pull exceeds Earth's gravitational hold on it. Things leave. The oceans go first because water has no tensile strength. Water cannot resist being pulled. The ocean surface on the Saturn-facing hemisphere lifts away from the basin that has contained it since Earth had oceans. Not as a wave, not as a surge, but as a sustained rise, the water climbing through the sky in a column that stretches towards Saturn. As the water rises above Earth's diminishing atmosphere, the pressure drops, the temperature drops, and the water transitions from liquid to vapor to ice crystals. The column disperses into the orbital space between the two bodies. Most of it does not reach Saturn. It enters orbit, a diffuse cloud of water and ice that will eventually settle into a ring or fall inward over millions of years. The atmosphere follows. Nitrogen and oxygen and argon that have surrounded this world for billions of years stream outward in a luminous plume visible from Titan's surface as a faint brightening of the space between Saturn and the approaching debris. The tectonic plates, the enormous rigid pieces of lithosphere that have been grinding against each other in a slow dance for hundreds of millions of years, separate. The mantle, released from the pressure balance that maintained its coherence, partially erupts through the fractures and disperses into the debris field. The iron core holds longest, dense, gravitationally self-cohesive, held together by the strength of metallic bonds under the compression of its own mass. The core survives the unbinding of everything above it. It falls, a sphere of iron and nickel approximately 2,500 kilometers in radius, moving through a debris field that was, hours earlier, a planet. There is no impact. The core enters Saturn's outer atmosphere and begins to descend. The physics is not interested in the distinction between these two things. Neither is Saturn. the oceans leave in weeks. Total volume of Earth's oceans, 1.335 billion cubic kilometers. This water has been cycling through or near this planet's surface for approximately 4.4 billion years. It arrived partly from within, volcanic outgassing during Earth's early formation, releasing water vapor that condensed as the surface cooled, and partly from without, delivered by water-bearing asteroids and comets during the period of late heavy bombardment. It has cycled continuously since, through the hydrological cycle of evaporation and precipitation at the surface, through the slower geological cycle of subduction at tectonic boundaries and release through volcanism, through the even slower process by which water is locked into hydrated minerals in the crust and mantle, and eventually released again over millions of years. Specific volumes. Pacific Ocean, 710 million cubic kilometers. Surface area, 165 million square kilometers. Maximum depth, 10,935 meters at Challenger Deep, which received its first human visitors in 1960 and has been reached directly fewer than 20 times since. Atlantic Ocean, 310 million cubic kilometers. Surface area, 106 million square kilometers. Average depth, 3,332 meters. Indian Ocean, 264 million cubic kilometers. Arctic, southern, and marginal seas, approximately 50 million cubic kilometers combined. In the months before the Roche limit crossing, Saturn's tidal differential drives ocean mass steadily toward the Saturn-facing hemisphere. The ocean does not simply slosh in a tide, it migrates. Mass moves laterally across ocean basins as the gravitational gradient pushes water toward one side of the planet. The Atlantic, shallower than the Pacific and with less total mass, responds more rapidly. The North Atlantic drains toward equatorial regions. The Pacific, deepest and most massive, sustains its structure longest. Coastlines on the Saturn-facing hemisphere flood with ocean water migrating from the opposite hemisphere. Coastlines on the away-facing side expose continental shelves as the water recedes. These changes occur over weeks to months, not as a storm, not as a surge, but as a gravitationally driven redistribution for which Earth's geological record has no precedent. At the Roche limit crossing, Saturn's tidal gradient at Earth's surface exceeds Earth's surface gravitational acceleration of 9.8 meters per second squared. Water, which has no tensile strength and cannot resist being pulled, responds immediately. The ocean surface on the Saturn-facing hemisphere lifts, not metaphorically, physically rises from its basin as the net force on the water becomes directed away from Earth. The water enters the column forming above it, dispersing rapidly in the near vacuum as Earth's atmosphere thins. The Pacific Ocean, 710 million cubic kilometers, evacuates over a period of 2 to 4 weeks from the initial Roche crossing. Its departure is not instantaneous. The rate of outflow depends on the tidal differential at each moment, which increases as Earth continues towards Saturn. The ocean floor of the Pacific, exposed for the first time in the roughly 180 million years since the current Pacific Basin formed, lies open. The mid-ocean ridges, the abyssal plains, the hadal trenches, the hydrothermal vent communities that have existed independent of sunlight for millions of years, exposed to vacuum. The Atlantic follows over the same timescale. Earth's surface, dry for the first time in 4.4 billion years, remains dry for approximately 72 hours. Then the crust begins to fracture. Earth's atmosphere has a total mass of approximately 5.15 times 10 to the power of 18 kilograms. Nitrogen, 78.09%. Oxygen, 20.95%. Argon, 0.93%. Carbon dioxide, water vapor, methane, and trace gases together form a fraction of a percent. The total mass of the atmosphere is less than 1/1,000,000th of Earth's total mass, but it is the layer that moderates surface temperature, maintains the pressure necessary for liquid water to exist at the surface, absorbs ultraviolet radiation in the stratospheric ozone layer, carries weather and climate patterns, and makes breath possible for every organism that has ever breathed. The atmosphere is structured in layers with different temperature profiles, densities, and compositions. The troposphere, extending from the surface to roughly 12 kilometers altitude, contains approximately 80% of all atmospheric mass and essentially all weather. The stratosphere, from 12 to 50 kilometers, contains the ozone concentration that absorbs solar ultraviolet radiation. Above this, the mesosphere and thermosphere extend to the formal boundary with space, the Kármán line at 100 kilometers, above which the atmosphere is too thin to provide meaningful aerodynamic lift. The upper layers of the atmosphere are already lost continuously to space in small quantities through atmospheric escape. Individual molecules moving fast enough to exceed Earth's escape velocity leave without returning. This process has been operating throughout Earth's history, balanced by volcanic outgassing and other sources. The rate is ordinarily negligible over human timescales, a slow leak, not a hemorrhage. As Saturn approaches and tidal forces increase, the rate of upper atmospheric escape accelerates. The thermosphere and exosphere thin. The upper stratosphere begins to dissipate. As the Roche limit crossing occurs and tidal forces exceed surface gravity, the process accelerates from both ends simultaneously. The upper atmosphere escaping upward into space, the lower atmosphere being drawn upward by the tidal gradient into the column that the ocean has already partially vacated. The departure of the troposphere, the layer where everything that breathes has always lived, takes hours after the Roche crossing. This is the part that should be held without comfort. The atmosphere does not leave an empty world. The sequence of departure and the sequence of life's elimination at the surface are not cleanly separated. The atmosphere does not wait for the surface to be cleared before leaving. Organisms that breathe, everything that has ever used oxygen, from the first aerobic bacteria to the last complex animal, experience the pressure falling without any physiological framework for what is happening, because nothing in the history of life on Earth has prepared any organism for this. The oxygen in that atmosphere was released by photosynthetic organisms over approximately 2.4 billion years, accumulated from near zero concentration, to the 21% that has characterized Earth's atmosphere for the past 500 million years. The nitrogen cycled through living systems in an endless loop from the beginning of life. The carbon dioxide was regulated by biological and geological processes across geological timescales. All of it streams outward in the tidal column. It disperses into the space between Earth and Saturn, drifting through the outer solar system as diffuse molecular gas over decades and centuries. It will be indistinguishable from the interplanetary medium within decades. It was breathed once. That fact has no physical consequence in what follows. It is simply true. In 1610, Galileo drew Saturn incorrectly and never understood what he had seen. In July of 1610, Galileo Galilei turned a telescope toward Saturn for the first time. Galileo had been systematically observing the sky with his improved telescope for less than a year. In January of 1610, he had discovered that Jupiter had 4 moons orbiting it, objects that had never been observed before, because no instrument capable of resolving them had existed before his telescope. He published the discovery in the Sidereus Nuncius and dedicated it to the Medici family. The revelation that celestial bodies could orbit something other than Earth was significant in the context of the astronomical debates of the time. When he turned the telescope to Saturn, he expected to see what he had seen with every other planet, a point of light resolving into a disk. He saw something more confusing. Saturn appeared to be composed of 3 bodies. A central disk, flanked on either side by 2 smaller forms, pressed close, symmetrically arranged, each roughly a third of the brightness of the central body. He could not determine what he was looking at. No astronomical framework available to him could accommodate a triple planet. He encoded his observation as a Latin anagram, a practice among natural philosophers of the era for establishing priority in a discovery while delaying public announcement, and sent it to Johannes Kepler. Rearranged, the anagram read, "I have observed the highest planet, triple-bodied." He concluded he had found 2 large moons in an unusual configuration, different from Jupiter's moons, in that these seemed fused against the planet's disk, rather than orbiting freely. In 1612, the flanking bodies disappeared. Galileo looked at Saturn and found a perfect sphere. The companions had vanished without explanation. He wrote that it seemed Saturn had devoured its own children, a reference to the mythological Cronus, Saturn, who consumed his offspring, and he turned to other problems, troubled and without resolution. In 1613, the companions returned. He observed them again and could still not determine their nature. What Galileo was seeing were rings. Saturn's rings are extraordinarily thin, between 10 meters and 1 kilometer deep in most regions, for a structure spanning 282,000 kilometers in width. When Earth's orbital position relative to Saturn places the viewer near the plane of the rings effectively disappear. A structure 1 kilometer thick, viewed edge-on from a distance of hundreds of millions of kilometers, falls below the resolving power of any instrument Galileo had. When Earth's orbital position provides a favorable viewing angle, the rings appear as the flanking bodies he observed. The rings were correctly identified by Christian Huygens in 1655, observing with a more powerful telescope and devoting sustained attention to Saturn's changing appearance over months. He, too, encoded his conclusion as an anagram before publishing fully in 1659. Giovanni Cassini, in 1675, identified the dark gap in the ring system now called the Cassini division, a 4,800-kilometer band cleared by the gravitational resonance of Saturn's moon Mimas, which orbits at half the period of ring particles in that zone. Galileo died in 1642 under house arrest, convicted of heresy for supporting the Copernican model of the solar system. He never resolved what he had seen. He drew it carefully. He labeled it uncertain. The label was accurate. Some of what we are looking at now will also need that label. Saturn's rings are younger than the last dinosaurs. The rings look ancient. In any image, from a spacecraft, from a professional observatory, from a backyard telescope on a steady night with adequate aperture, Saturn's rings appear to be a permanent and fundamental feature of the outer solar system. The instinct to assign them great age is merely irresistible. They look like something that was there at the beginning and will remain until some inconceivably remote ending. In 2019, a team of researchers published an analysis of gravitational data collected by the Cassini spacecraft during the final phase of its mission, when it made 22 close orbital passes between Saturn and its innermost rings. The mass and density distribution of the rings, revealed by these measurements with unprecedented precision, allowed the team to calculate the rings' approximate age from the rate at which they accumulate micrometeorite contamination and lose mass to ring rain. The rings are between 10 million and 100 million years old. The solar system is 4,500 million years old. Saturn's rings have existed for, at most, approximately 2% of the solar system's history. They appeared, in geological terms, very recently. The non-avian dinosaurs that went extinct 66 million years ago were alive before some versions of this age estimate place the rings' formation. The first members of the genus Homo were walking on Earth's surface before the upper end of this estimate. The rings were not present for the majority of the history of complex life on Earth. The leading hypothesis for the rings' origin is that a medium-sized icy moon, perhaps between 1,500 and 3,000 kilometers in diameter, drifted too close to Saturn through mechanisms that are not fully understood, crossed the Roche limit, and disintegrated. The moon's water ice dispersed into the orbital band we now see. The moon's denser rocky material sank towards Saturn. The moon's name is not known because the moon no longer exists in any form that can be examined. We know a moon disintegrated because the rings are here. We do not know which one. The rings are also disappearing. Ring particles drift inward, drawn by the interaction between their electrical charge and Saturn's magnetic field, in the process called ring rain. Material falls into Saturn's equatorial atmosphere continuously, the rate measured by Cassini at thousands of kilograms per second. In another 100 million years, possibly less, the rings will be gone. Saturn will return to the bare state it occupied for its first 4 billion years. We are observing the rings during the narrow window in which they exist. Before we were here, no rings. After we are long gone, no rings. Between those two absences, this. We look up on a clear night and we see them. And that looking at this particular moment in a 4 billion year history of a planet without rings is the only moment there has ever been to look. Iron falls through 30,000 kilometers of something no laboratory has ever sustained. Hold a piece of iron. Not a finished object, a rough piece of iron ore pulled from rock that formed during Earth's early geological history. The first thing you notice is its weight. Denser than granite, denser than most rocks handled in ordinary life, cold to the touch, because iron conducts heat away from skin more efficiently than most materials. It looks unremarkable. It looks like something from the ground, which is exactly what it is. Iron is the end point of stellar nucleosynthesis. Stars burn hydrogen into helium through the proton-proton chain. Stars more massive than the Sun burn helium into carbon through the triple alpha process. More massive stars burn carbon into oxygen and neon and magnesium, continuing up the periodic table through silicon and sulfur and argon and calcium. At each step, energy is released, the energy that powers the star and holds it against gravitational collapse. But this energy release ends at iron. Iron 56 is the most stable nucleus per nucleon. It is the bottom of the nuclear binding energy curve. Fusing iron requires energy rather than releasing it. When a massive star builds an iron core, the nuclear burning cannot continue. The core collapses. The outer layers fall inward and then rebound in a supernova. Iron is the wall at the end of stellar alchemy. Everything heavier than iron was made in the collapse itself or in the collision of neutron stars. Earth's core is approximately 85% iron by mass. The inner core, solid, roughly 1,220 kilometers in radius, sits at pressures exceeding 360 gigapascals and temperatures around 5,700 degrees Celsius, comparable to the Sun's surface. The outer core, surrounding it in a liquid shell about 2,200 kilometers thick, is iron and nickel in vigorous convective motion. That convection generates Earth's magnetic field, which has shielded the surface from high-energy solar particles for billions of years. In the Roche limit crossing, the core is the last part of Earth to lose coherence. The ocean is gone. The atmosphere is gone. The crust has fractured and dispersed. The mantle has separated into fragments. The core's own gravity, combined with the strength of metallic bonds under its own compression, maintains its integrity past the point where everything else has unbound. A sphere of iron, roughly 2,500 kilometers in radius, falls through a debris cloud that was, hours ago, a planet. Then it enters Saturn's outer atmosphere. Cold hydrogen gas at low density at the visible cloud tops. The core falls through it, compressing the hydrogen below it as it descends, the surrounding material offering resistance through density rather than through solidity. Deeper, 10,000 kilometers below the clouds, supercritical hydrogen, neither gas nor liquid in the familiar sense. Still the core descends, still coherent, heating from compression. At 20 to 30,000 kilometers depth, metallic hydrogen. Here is the transition that has no equivalent anywhere in human experience. Iron, already stripped of its outer electrons by the extreme pressure and temperature, meets hydrogen equally stripped, its single electron liberated into the surrounding electron fluid. Two electrically conductive materials at pressures of millions of atmospheres and temperatures of tens of thousands of degrees, meeting at a boundary that blurs within centuries and vanishes within millennia as convection mixes the materials. The iron does not stop. It continues downward toward the center we cannot see. It arrives carrying 4.5 billion years of Earth's geological history encoded in its isotopic composition and crystal structure. Information that, at those pressures and temperatures, is immediately and permanently erased. One ice crystal from Earth's Antarctic Circle Saturn for the next billion years. Begin with a specific thing. One ice crystal, formed in the polar stratosphere above Antarctica on a winter night in the recent past, perhaps 50 years ago, perhaps 100. A hexagonal lattice of 18 water molecules assembled from vapor at temperatures of minus 80 degrees Celsius, no larger than a grain of fine sand. It fell slowly through the stratospheric air, eventually joining the surface of the Ross Ice Shelf, compressed under subsequent snowfall, locked into glacial ice that had been accumulating and moving for hundreds of thousands of years. The water molecules in this crystal have cycled through the hydrosphere, atmosphere, and cryosphere many times in their history. The oxygen 18 to oxygen 16 ratio in the crystal encodes the air temperature at the time it formed, a record no one will read. When Saturn's tidal forces begin stripping the Antarctic ice sheet, this crystal is among the mass that lifts. The sheet, kilometers thick over most of the continent, responds to the gravitational gradient. The crystal, locked in ice that now behaves as a fluid under tidal stress, lifts. Above the dissipating atmosphere, the specific trajectory it follows, determined by the approach geometry, the angle, the velocity, does not carry it into Saturn. It carries it into orbit. It enters a ring. Around it, rock fragments from granite mountain ranges that took 100 million years to uplift. Silicate minerals from the Pacific floor, basalt crystallized at mid-ocean ridges over 200 million years. Iron oxide from desert soils, calcium phosphate from the bones of every vertebrate that ever lived. Carbon compounds from 4 billion years of biology, from the first replicating molecules to the last complex organisms. Nitrogen from the atmosphere. Oxygen that was, until recently, breathed. Over thousands of years, the debris cloud spreads along the orbital band, gentle particle-to-particle collisions at centimeters per second, distributing mass laterally. the clouds slowly flattening into the equatorial plane Saturn's gravity prefers. Over millions of years, the lightest molecular components, atmospheric nitrogen, water vapor, are swept away by Saturn's magnetosphere. What remains is ice, rock, and iron compounds. Over hundreds of millions of years, ring rain draws the material inward. The particles spiral slowly towards Saturn, falling into the equatorial atmosphere at thousands of kilograms per second. 1 billion years after the collision, the ring that was Earth is gone, absorbed into Saturn's upper atmosphere, mixed into the chemistry of its clouds, indistinguishable from everything else Saturn is made of. The ice crystal from Antarctica has, over the course of 1 billion years, circled Saturn approximately 70 billion times. Then it falls. Then it is gone. Saturn has been holding the same hexagon at its north pole since before human language existed. At Saturn's north pole, a jet stream traces the path of a perfect regular hexagon. Each of its 6 sides measures approximately 13,800 kilometers, longer than the full diameter of Earth. The hexagon spans 30,000 kilometers from one edge to the opposite side. At its center, a polar vortex rotates with a clearly defined eye approximately 2,000 kilometers across, and wind speeds at its wall exceeding 500 kilometers per hour. The entire hexagonal structure rotates in alignment with Saturn's interior magnetic field, not with the surface atmospheric winds, which drift at different rates, but with something deeper, anchored to Saturn's interior rotation. The hexagon was first photographed by the Voyager 2 spacecraft in August 1981. It appeared again in Cassini images beginning in 2004. Cassini monitored it continuously until the mission ended in September 2017. In 36 years of direct observation, and almost certainly for a period of unknown length before observation began, the hexagon maintained its shape, its scale, its rotational period, and its position without measurable change. The physics that produces it, a standing wave in the jet stream, generated by the resonance between Saturn's interior rotation rate and the differential velocities of atmospheric layers above it. Laboratory experiments with rotating tanks of fluid show that polygonal standing waves of this type, hexagons, pentagons, squares, depending on rotation parameters, emerge naturally from the mathematics of rotating fluid dynamics. The hexagon is not designed. It is not maintained by any mechanism. It is simply the configuration that the physics of Saturn's atmosphere at Saturn's specific rotation rate happens to prefer, stable enough to persist without change across timescales longer than any human institution. The hexagon is older than every building on Earth, older than every written language, older than agriculture, possibly as old as Saturn's current rotational configuration, which would make it billions of years old, a standing wave in a planetary atmosphere that has been turning since before the continents on Earth had recognizably modern shapes. In the collision scenario, the approach of Earth's mass perturbs Saturn's upper atmosphere. The tidal interaction, smaller than Earth experiences because Saturn is far more massive, but non-zero, drives waves through Saturn's jet streams. As Earth's debris enters the system and the collision proceeds, the new distribution of mass and heat in Saturn's atmosphere would interfere with the standing wave resonance that sustains the hexagon. The specific velocity ratios that produce a hexagon rather than a pentagon or a square would shift. The hexagon would become unstable and close. A new pattern would eventually emerge, determined by the altered atmospheric dynamics. We cannot calculate in advance what shape that would be. The new pattern would begin turning. And right now, as whatever pace sleep is bringing to your breathing, whatever space is opening between thoughts, the hexagon is turning, not as image, as fact, at Saturn's North Pole. At this moment, 30,000 kilometers wide, a standing wave in the atmosphere of a gas giant is completing another slow rotation. It has been doing this since before your species existed. It knows nothing about any of this. The collision releases more energy than the sun produces in 110 days. These are the numbers. Earth arrives at Saturn moving at roughly 35 kilometers per second. The speed an object gains falling from Earth's orbital distance into Saturn's gravitational field. The exact figure shifts with approach angle and trajectory. 35 kilometers per second is representative. At that speed, with Earth's mass, the kinetic energy released at collision is enormous in a way that standard comparisons stop working. Consider every nuclear weapon ever built, every device ever detonated in every test across every nation in history. The combined energy of all of it is a number so much smaller than this collision that the comparison barely registers. The collision releases something on the order of a quadrillion times more. The word quadrillion is correct. It doesn't help. A more useful comparison, the sun. The sun radiates energy in all directions simultaneously. A continuous output so large it lights and warms an entire planetary system from 90 million miles away. This collision releases energy equivalent to roughly 110 days of that total output. Not 110 days of sunlight hitting Earth, 110 days of everything the sun produces, in all directions, all at once. That energy does not concentrate in one place. It deposits across Saturn's upper atmosphere and the surrounding debris field. It heats gas to extreme temperatures, drives pressure waves downward through Saturn's atmospheric layers, and forces some of Saturn's own hydrogen outward into space. Some of that ejected material escapes entirely. Some forms temporary structures, loose rings, arcs of debris that eventually fall back. Over years and decades, the energy works its way outward as infrared radiation. Saturn brightens measurably in thermal wavelengths for years after the event, possibly decades. The permanent changes, once the thermal noise settles, Saturn's mass increases by about 1%. Its equatorial radius grows by roughly 200 kilometers. Its rotational period shifts by somewhere between a fraction of a second and several seconds per rotation. The exact amount depends on the angle at which Earth arrived and how much angular momentum it delivered. Its orbital period around the Sun changes by less than 1 second per year, because that period depends on the Sun's gravity at Saturn's distance, not on Saturn's own mass. The thermal disruption The new debris rings, the atmospheric turbulence, those fade over millions of years as Saturn settles around its new equilibrium. One planet absorbed. 1% gained. The Sun barely noticed. Enceladus has been erupting into Saturn since long before any of this begins. Before Earth arrives, before the approach, before the first unusual tide, Saturn's moon Enceladus is already doing something that should not, by simple thermodynamics, be possible. Enceladus is 504 kilometers in diameter. It is small enough to fit inside many countries. Its surface is almost entirely water ice, making it the most reflective body in the solar system. It returns approximately 99% of the sunlight that strikes it. At its distance from the Sun, and with that reflectivity, simple radiative equilibrium would predict a surface temperature well below minus 200 degrees Celsius. The entire moon should be frozen solid to great depth. The south polar region of Enceladus is approximately 90 degrees warmer than the surrounding surface. Not warm by any Earth standard, still deeply cold, but dramatically, anomalously warmer than the incoming solar energy can explain. The reason is tidal heating. Enceladus orbits Saturn in a slightly eccentric path maintained by an orbital resonance with the moon Dione. As Enceladus moves through this orbit, the magnitude and direction of Saturn's tidal pull on it changes continuously. The moon flexes. The friction of that flexing converts mechanical energy into heat. The heat melts ice in the lower interior. Beneath Enceladus's ice shell lies a global ocean of liquid water. This has been confirmed by multiple independent lines of evidence from Cassini, a wobble in Enceladus's rotation consistent with a decoupled ice shell floating on liquid, a gravitational signature indicating a mass deficit below the South Pole, consistent with a cavity filled with liquid water rather than ice, and the direct chemical sampling of what erupts through the ice. At the South Pole, parallel fractures in the ice shell, the tiger stripes, each roughly 130 kilometers long, vent material from the interior ocean directly into space. In 2005, the Cassini spacecraft flew through these plumes and analyzed them in situ. The plumes contain water vapor, ice particles, sodium chloride, silica grains, molecular hydrogen, carbon dioxide, methane, and complex organic molecules. The molecular hydrogen is produced by liquid water reacting with warm rock on the ocean floor. The same hydrothermal chemistry that powers life around thermal vents in Earth's deep ocean. Enceladus erupts several kilograms of material per second continuously into Saturn's magnetosphere. This material feeds Saturn's E-ring, the faint, diffuse ring that extends far beyond the main ring system in real time. Enceladus is constructing part of Saturn's ring system right now, powered by the tidal friction of Saturn's own gravity acting on a moon that cannot escape it. In the collision scenario, Enceladus survives. Its orbit is perturbed as Saturn's mass increases, and the gravitational configuration of the system changes. The eruptions continue, altered in intensity, feeding a ring system now made partly of Earth. Enceladus erupts because Saturn pulls it in a rhythm that has no intention behind it, and no awareness of what the friction produces. The pulling happens because mass is arranged in a particular way. The friction happens because the moon cannot be rigid. The heat happens because friction happens. The liquid water happens because of the heat. The organic chemistry happens in the liquid water. The eruption happens because the ocean is pressurized against an ice lid. It has been happening since long before we arrived. It will continue when the ring that was Earth has long since dissolved. We have never seen Saturn's center. The Cassini spacecraft arrived at Saturn in June 2004, 7 years after its launch from Cape Canaveral. It was approximately the size of a school bus. It carried 12 scientific instruments. It operated in Saturn's orbit for 13 years, completing 294 orbits of the planet and returning 635 gigabytes of data to Earth. In April 2017, the mission entered its grand finale phase, 22 orbital passes diving between Saturn's innermost ring and its upper atmosphere, closer to Saturn than any spacecraft had ever traveled. Cassini measured the gravitational field of Saturn and its rings with unprecedented precision during these passes. The data from these final orbits produced the 2019 determination of the ring's age. They also produced the most detailed picture yet of Saturn's interior mass distribution, revealing the extended fuzzy core rather than the compact solid core earlier models had predicted. On September 15th, 2017, Cassini was commanded into Saturn's atmosphere. The decision was deliberate and had been planned for years. The spacecraft was running low on propellant, and an uncontrolled drift created a possibility, small but non-zero, of eventually colliding with Enceladus or Titan, contaminating a potentially habitable world with Earth microorganisms. Planetary protection requirements demanded a controlled disposal. Cassini entered the atmosphere. Aerodynamic and thermal forces destroyed it within minutes. Its final signal, received at Earth after an 83-minute light travel delay, cut off in the middle of transmission. No spacecraft currently orbits Saturn. No spacecraft is currently en route to Saturn. The Dragonfly mission, a rotorcraft lander destined for Titan, is scheduled to arrive in 2034. It will study Titan's surface chemistry, not Saturn's interior. Various Enceladus mission concepts are in study phases. None will directly measure Saturn's deep interior in the foreseeable future. Everything we know about Saturn's center is inferred. The interior mass distribution inferred from Cassini's gravity measurements suggests heavy elements distributed in a gradient, extending perhaps 60% of Saturn's radius outward from the center, rather than concentrated in a compact rocky core. What phase of matter exists at the geometric center, what the pressure is, what the temperature is, whether there is a meaningful distinction between the different materials present at those conditions, is calculated from equations of state for matter under extreme conditions, validated against laboratory experiments conducted for fractions of a second at pressures far below those at Saturn's center. The equations are good. Equations are good until an experiment shows otherwise. For Saturn's center, the experiment has not been run. When Earth's iron core descends through Saturn's metallic hydrogen layer and reaches whatever is at Saturn's center, it joins something we have not seen. After the collision, the system we had partially characterized becomes one we have not characterized at all. The center of Saturn is unknown. After Earth arrives, it is still unknown. It will remain unknown. Nothing on Earth survives to witness what Earth becomes. Every account of a planetary collision, in every popular format, in every visualization, including this one, carries a hidden assumption. There is a perspective, an eye, a vantage from which events unfold and are described. The language of description implies observation. The oceans rise, the crust fractures, the core descends. These phrases have a camera built into them. There is no camera. There is no eye. By the time Earth crosses the Roche limit, the surface has been uninhabitable for months. The preceding sequence, seismic disruption from tidal flexing at scales that exceed Earth's entire geological record, ocean migration and flooding on the Saturn-facing hemisphere with no historical precedent, atmospheric disruption as tidal forces alter pressure gradients and wind patterns globally. The departure of the Moon from Earth's gravity would have destroyed every piece of human-built infrastructure. Every structure, every data center, every telescope, every satellite in low Earth orbit, every radio array. The capacity to observe, record, or transmit any information about the final sequence would have been eliminated before the final sequence begins. There is an observer in the Saturn system. It is on Titan. Titan orbits 1,221,870 kilometers from Saturn's center, far enough from the collision zone that the gravitational disruption would perturb its orbit significantly, but not eject it. Its surface temperature is minus 179 degrees Celsius. Its lakes are liquid methane. Its orange atmospheric haze, built from complex organic photochemistry in the stratosphere, drifts in a nitrogen sky. The Huygens probe that descended through Titan's atmosphere in January 2005 and transmitted from the surface for 72 minutes before its battery died is still there, inert on the surface of a moon orbiting Saturn. Nothing on Titan is watching. The Cassini spacecraft that might have observed the collision from within the Saturn system was deliberately destroyed in Saturn's atmosphere on September 15, 2017. No other spacecraft is present. The event occurs without documentation. A planet that spent 4.5 billion years as a world, hosting oceans, continents, an atmosphere with weather and seasons, and for the last 3.8 billion years, life in forms ranging from single-celled organisms to everything that followed, disassembles itself in the tidal field of another planet. The orbit that Earth occupied continues to exist as a gravitational path in the Sun's field, with nothing moving along it. No signal is sent. No image captured. No voice describes it as it happens. It simply happens, in the cold, in the silence that is the natural state of the vast majority of everything that exists. A planet, alone, becoming something else, with nothing anywhere nearby to note the transition. That silence is not a poetic choice. It is the condition. The carbon in your bones was already ancient when Earth formed. Begin with carbon leaving. After the collision, some fraction of the carbon that was Earth's, in the organic molecules of soil, in the structural chemistry of every organism that ever lived, in the accumulated biological residue of 4 billion years, disperses with the rest of Earth's material. Some enters Saturn's atmosphere and descends, eventually mixing into the chemistry of Saturn's clouds. Some enters the debris ring and orbits for millions of years. Some, carried in light organic molecules, drifts outward into the interplanetary medium and is eventually swept beyond the Saturn system. Follow that carbon backward. A carbon atom that was, until recently, part of a bone in a vertebrate animal. Before the bone, it was part of food that built the organism, that contained the bone. Before the food, it was part of a plant, a carbon dioxide molecule pulled from the atmosphere through a leaf, converted by photosynthesis into organic carbon, incorporated into the cellulose or starch or protein of the plant structure. Before the atmosphere, it was exhaled by another organism. Before that, metabolized from organic compounds. Before that, part of another organism's structure. The chain extends continuously backward through 4 billion years of biological cycling. The same carbon atoms have been incorporated into living things and released, incorporated and released across the entire span of life on Earth, from the first replicating chemistry in warm early ocean chemistry to the last complex organism on the last habitable day. Go further back, before life. That carbon was not made on Earth. Carbon cannot be synthesized on Earth or in the sun. The sun burns hydrogen into helium, and late in its life will burn helium into a small amount of carbon. But it is not massive enough to sustain the process that produces carbon in large quantities. The triple alpha process, in which 3 helium nuclei fuse into a single carbon-12 nucleus, occurs in the interiors of stars at least 1.5 times as massive as the Sun, during the red giant or asymptotic giant branch phases of their evolution, where temperatures and pressures are sufficient for the reaction to proceed at a meaningful rate. When those stars end their lives, in planetary nebulae if they are modestly massive, scattering their outer envelopes into the surrounding space, in supernova if they are more massive, exploding and seeding large regions of the galaxy with their processed material, the carbon they synthesized disperses into the interstellar medium. It drifts in cold molecular clouds, sometimes for hundreds of millions of years, in conditions where the temperature is only a few degrees above absolute zero, and the density is low enough that chemical reactions are extremely slow. Eventually, triggered by a nearby stellar explosion, by a gravitational instability, by a collision between clouds, a region of the cloud collapses. A new star ignites at the center. A disk of gas and dust forms around it. Planets accumulate from the disk. The carbon from the dead star is incorporated into the planetesimals, into the growing planets, into the world that eventually becomes the place where things use carbon to replicate, to metabolize, to build structures, to move. The carbon in you was made in a star that died before the sun ignited. It drifted through cold space for a period that may have been longer than the current age of the solar system. It was incorporated into Earth's early chemistry. It cycled through 4 billion years of life. Saturn does not destroy it. Saturn redistributes it. The carbon continues in whatever form the physics of its new location allows, as it has always continued through the death of stars and the formation of worlds, because carbon does not stop being carbon when the structures it inhabits dissolve. From a single iron atom to the mass of a world, what Saturn's interior receives. Begin with a single proton. One hydrogen nucleus, a single proton, no electrons, moving at a velocity corresponding to the temperature of Saturn's metallic hydrogen layer, approximately 10,000 degrees Celsius, existing at a depth of roughly 25,000 kilometers below Saturn's visible cloud tops, at a pressure of approximately 2 million times Earth's sea level atmospheric pressure. This proton is indistinguishable from the 10 to the power 57 other protons surrounding it in the metallic hydrogen layer. It has no identity that physics can assign to it. It moves in response to pressure gradients and electromagnetic forces, contributing to the convective flow that generates Saturn's magnetic field. It has been doing this for approximately 4.5 billion years. Earth's debris arrives in layers. The first material from Earth to penetrate to significant depth in Saturn is not the iron core, which falls more slowly. It is the lightest material, hydrogen from Earth's thin upper atmosphere, dissociated by the extreme conditions of Saturn's upper layers, mixing into Saturn's own hydrogen within seconds of contact. This material is, physically, indistinguishable from Saturn's hydrogen the instant it mixes. Earth's atmospheric hydrogen joins Saturn's atmospheric hydrogen. There is no boundary. There is no record. Below this come Earth's silicate minerals, the rock from the crust and upper mantle, which enters Saturn's atmosphere as fragments and vaporizes at extreme temperatures deep in the atmospheric layers. Silicon, oxygen, magnesium, aluminum, the atoms of Earth's continental and oceanic crust, dissolve into Saturn's interior. Being heavier than hydrogen and helium, they drift downward through the layers for buoyancy, gradually enriching the concentration of heavy elements in Saturn's deeper interior. This process takes thousands of years per layer as convection slowly mixes the infalling material. Below this, finally, comes Earth's iron core, moving more slowly than the debris field around it, maintaining coherence through the tidal forces that dispersed everything else, arriving at the metallic hydrogen boundary as a coherent mass, before gradually dissolving as pressure and temperature strip the iron of its electron structure and make it indistinguishable from the surrounding conducting fluid. The scale of this sequence spans 50 orders of magnitude, from a single proton 10 to the negative 15th meters in diameter to the mass of a world, 5.972 times 10 to the 24 kilograms, arriving and being absorbed. At every scale, the same physical laws govern the process. The proton does not know that more mass is coming. The mass does not know where it is going. The interior of Saturn receives both with the same indifference that it has received everything else for 4.5 billion years. From Saturn's perspective, if such a perspective had meaning, the addition of Earth is a small perturbation in an ongoing process of slow internal evolution. The convection patterns that generate the magnetic field adjust over centuries. The temperature gradient through the interior changes by fractions of a percent. The boundary between the fuzzy core and the metallic hydrogen layer, already not a sharp boundary, becomes slightly less sharp as more heavy material mixes into the surrounding layers. From outside Saturn, at the orbital distance of the nearest star, the event produces no detectable change. The proton in the metallic hydrogen layer continues moving. It doesn't know that a planet has joined it. It simply moves, as it has always moved, carried by currents that have been flowing for longer than Earth existed. Titan keeps going. Titan orbits Saturn at 1,221,870 kilometers from the planet's center. Its orbital velocity is approximately 5.6 kilometers per second. Its orbital period is 15.9 Earth days. It has maintained this orbit for approximately 4.5 billion years through every change in the Saturn system, through the formation and disappearance of previous ring systems, through the disruption of whatever moon became the current rings 10 to 100 million years ago. In the collision scenario, Titan's orbit is perturbed significantly. The approach of Earth's mass changes the gravitational configuration of the Saturn system. And as Earth's material is absorbed into Saturn and the system's mass distribution shifts, Titan's orbital eccentricity increases. Its path around Saturn becomes more elliptical, closer at some points, farther at others. This eccentricity changes the strength of Saturn's tidal forces on Titan across different points in the orbit, altering the tidal heating that keeps Enceladus active, and that also contributes to Saturn's interaction with all its moons. Over millions of years, tidal interactions between Titan and Saturn damp the new eccentricity. Titan settles into a slightly different orbit from the one it occupied before. Its period changes by a small amount. Its average distance from Saturn shifts slightly. The effect on Titan's surface and interior is modest, a change in the intensity of tidal heating, a shift in how rapidly the ice shell is processed, a small change in the rate of any geological activity. The methane lakes persist. The nitrogen atmosphere persists. The complex organic photochemistry in the stratosphere persists. Titan is the only moon in the solar system with a substantial atmosphere. Its surface pressure, 1.467 times Earth's sea level pressure, is higher than Earth's, despite Titan's far smaller gravity, because the atmosphere is cold and dense. The nitrogen that constitutes 98% of it has been there for as long as Titan has existed, maintained by whatever internal processes and external inputs balance the slow atmospheric escape. The methane, which would be depleted by photochemical reactions on timescales of tens of millions of years without replenishment, is likely supplied continuously by some internal source, possibly cryovolcanism, possibly the breakdown of methane clathrates in the ice shell. Kraken Mare, 400,000 square kilometers of liquid methane and ethane on Titan's north polar region reflects whatever light reaches it from the distant sun. It is fed by methane rain falling from stratospheric clouds, draining through channel networks that Cassini's radar imager mapped from orbit over 13 years. The Huygens probe descended through Titan's atmosphere in 2005 and photographed rounded ice pebbles on the surface. Rounded, the scientists concluded, by the flow of liquid hydrocarbons, the same process that rounds river stones on Earth, replicated in a fluid 270 degrees colder. In the collision scenario, Kraken Mare continues to receive methane rain. The ice pebbles on the surface where Huygens landed continue to weather slowly in the orange methane wind. Titan does not know what happened in the inner reaches of Saturn's system. It does not know what Earth was, or that fragments of it now orbit Saturn in a ring that is itself slowly falling inward. It is not patient in the way that implies endurance. It is continuous in the way that all things without intention are continuous, simply persisting through the physics of its situation, as it has always persisted, as it will continue long after the ring that was Earth is gone. The methane rain falls. Saturn after. What stayed and what shifted. Saturn absorbed Earth. Not metaphorically, structurally. Earth's mass fell into Saturn's gravity well and did not come back. And yet, if you could measure Saturn before and after and set the two measurements side by side, the difference would be almost invisible. Saturn is roughly 95 times Earth's mass. Earth added one more. That's an increase of just over 1%. Less than rounding error in the scale of what Saturn already was. The rings were not 95 Earths. They were ice and rock, a fraction. The atmosphere was not 95 Earths. It was mostly hydrogen and helium, elements that weigh almost nothing at the densities that matter at planetary scale. Saturn's mass is concentrated inward, in a core that we still don't fully understand, possibly solid, possibly a kind of ultra-compressed fluid, possibly both at different depths. Earth would have added to whatever that is. Earth is rock and iron, dense, heavy. 1%, that's what a whole planet contributes to Saturn. The orbit around the Sun would have changed, but barely. Saturn takes about 30 years to complete a single circuit. After absorbing Earth, it would take something like 30 years and a few weeks longer. The Sun's gravity is the dominant force in that equation by a margin that makes one Earth and even 1% more Saturn essentially irrelevant. The orbit adjusts, but the adjustment is smaller than the uncertainty in our own orbital measurements. What wouldn't change? The tilt. Saturn's axis sits at about 27 degrees, similar to Earth's 23. Seasons on Saturn, if you can call them that, exist because of this tilt. A collision at a non-perpendicular angle would alter the tilt, possibly sharply, but the axis itself recovers on long timescales through gravitational interaction with the Sun and with Saturn's moons. Earth's contribution to that process is small enough to average out over centuries. What wouldn't change? The magnetosphere. Saturn has a magnetic field generated deep in its interior by the motion of metallic hydrogen under extreme pressure. Earth has a different kind: iron core, convection, magnetic dynamo. When Earth's material reaches Saturn's interior, it heats, compresses, and eventually loses whatever magnetic identity it had. It becomes part of Saturn's system. The field continues, slightly altered, over timescales long enough that no instrument could isolate the change. The moons would shift, the inner moons especially, Mimas, Enceladus, Tethys, would feel the increase in Saturn's gravity through subtle changes in the resonances that govern their orbits. Resonance is sensitive. Orbital ratios that were stable for billions of years might drift slightly out of alignment, then lock into new ratios. This process takes millions of years, but it would happen. Titan would be disrupted significantly. Titan, Saturn's largest moon, is the one object in Saturn's system massive enough to have its own gravitational personality. It carries a thick atmosphere. It has lakes. The change in Saturn's gravity would alter Titan's orbit, not dramatically, but measurably over geological time. What effect that has on Titan's atmosphere and surface is genuinely uncertain. 1% more Saturn, 30 more Earth days per orbit, slightly reshaped resonances among the inner moons, a magnetosphere continuing without interruption, a tilt recovering over centuries. The universe does not register the loss of a planet the way a ledger registers a missing entry. It adjusts, redistributes, and continues. Earth was always a small number in a very large equation. Somewhere in this galaxy, a planet has already become someone else's rings. The Milky Way contains between 100 billion and 400 billion stars. Exoplanet surveys, the Kepler mission, which monitored 150,000 stars for 4 years and found thousands of planetary systems. The TESS mission, currently monitoring the nearest and brightest stars, consistently show that planets are common. The average star has at least one. Most have several. The total number of planets in the Milky Way is estimated in the hundreds of billions, with some analyses placing the number above 1 trillion. The galaxy is 13.6 billion years old. Some stellar systems have been evolving for 3 times as long as our solar system. 3 times as long for gravitational dynamics to perturb planetary orbits. 3 times as long for rare events to accumulate. 3 times as long for outer giant planets to evolve in ways that scatter inner rocky worlds onto crossing trajectories. Planetary collisions are not exceptional events in the history of planetary systems. The evidence in our own solar system is substantial. The giant impact that formed Earth's moon approximately 60 million years after the solar system's formation. The collision that stripped Mercury of most of its mantle, leaving a planet with a core comprising 85% of its radius. The event that tilted Uranus 97.8 degrees onto its side. The disintegration of a moon of Saturn sometime in the last 100 million years to create the current ring system. Each of these is inferred from physical evidence that remains in the objects we study today. The early solar system was violent in ways the current orderly arrangement of planets does not communicate. In systems older than ours, and in systems that formed in denser stellar environments, where stellar flybys were more common and gravitational perturbations more frequent, collisions between rocky worlds and gas giants may have occurred at rates higher than in our system. the observational signature, viewed from Earth, of a rocky planet falling into a gas giant, a brightening of the star's infrared emission, the gas giant radiating excess heat as it absorbs the kinetic energy of the impact, lasting for years to decades before gradually returning to baseline. This signature would be subtle. It would be indistinguishable in most archival datasets from stellar variability, from changes in the circumstellar dust, from instrument effects, from any of the dozens of other phenomena that cause stars to vary in the infrared. We have been monitoring stellar infrared emission systematically for decades. Some of the light in those archives has been traveling for hundreds of light years. Some of the stars in those data sets are in systems 3 times older than ours. We do not know how to identify this specific signature reliably. Somewhere, a planet that had surface chemistry complex enough to have generated life, or complex enough that it might have, became the ring of a gas giant. The ring it became may still be there, slowly falling into the planet that received it, or it may already be gone. The star it orbits may be one we have catalogued. The data from that system may already be in an archive on Earth. We are looking at those stars. We do not know which one. The solar system continues with 7 planets. The sun rises on Mercury the next morning. 8 minutes and 20 seconds of light travel time from the photosphere to Mercury's surface. The same interval it has always been. The same light, falling on the same heavily cratered landscape. Mercury completes its 88-day orbit. Venus, covered in its permanent cloud deck of sulfuric acid droplets, continues absorbing sunlight on its slow 243-day retrograde rotation. Its surface temperature, held at 465 degrees Celsius by the densest atmosphere of any rocky planet in the solar system, does not change. Mars completes another day in its 687-day orbit. Its thin carbon dioxide atmosphere, 95 times thinner than Earth's, continues its seasonal cycle with partial freezing at the poles in winter and sublimation in summer. Phobos and Deimos, its 2 small captured moons, orbit without change. Jupiter generates more internal heat than it receives from the sun and radiates the excess into space in all directions, as it has been doing for 4.5 billion years. The Great Red Spot, a storm larger than Earth, observed continuously since the 17th century, continues rotating within Jupiter's southern hemisphere. Jupiter does not register the loss of the 3rd planet. Neptune, at the solar system's outer edge, continues its 165-year orbit. Pluto, reclassified but still present, continues its 248-year elliptical path that at its closest brings it inside Neptune's orbit. The asteroid belt, unchanged. The Kuiper belt, unchanged. The Oort cloud, the vast spherical shell of icy bodies extending perhaps 1 to 2 light-years from the Sun, unchanged. A comet in the outer Oort cloud that has not entered the inner solar system in 80 million years continues its slow elliptical arc, unperturbed. The Voyager 1 spacecraft, launched in September 1977, now more than 23 billion kilometers from Earth and moving at approximately 17 kilometers per second into interstellar space, continues transmitting on its low-power signal, 23 watts, roughly the power of a refrigerator light bulb, across an unimaginable distance. There is no one in the inner solar system to receive it. It transmits anyway. A gravitational wave detector far more sensitive than any that currently exists would detect a faint signal from the collision, a ripple in space-time produced by the orbital inspiral of two massive bodies. The signal would be unmeasurable at the distance of the nearest star. It would fade to nothing within the Saturn system itself within years. No information about what happened travels beyond the solar system. The solar system has 7 planets. It had 8. The carbon that was in the 8th, that had been cycling through life and rock and ocean for 4 billion years on that 8th planet, is now in Saturn's rings and Saturn's atmosphere and the outer solar system. It has not stopped being carbon. It has not stopped being part of the same universe that contains the 7 planets that remain, and the star they orbit, and everything else that has ever existed. The same carbon is in you right now, made in the same kinds of stars, cycled through the same kinds of processes, present in this moment because the physics of this particular universe allows carbon to persist through everything that has happened so far. The universe is holding all of this together tonight. It has been doing so for 13.8 billion years. It will continue. What the rings become over the next billion years. At the moment the debris field settles into orbit, when the material that was Earth has found its equilibrium altitude around Saturn, when the gentle collisions between particles have begun flattening the cloud into a disk, the ring that Earth has become is unlike Saturn's existing rings in almost every way. It is not a pale, ordered disk of water ice. It is a dispersed cloud of heterogeneous material, ice mixed with silicate rock, mixed with iron compounds, mixed with complex organic residue from 4 billion years of biology. The particles range from dust grains to fragments the size of apartment buildings. They are distributed in an orbital band that has not yet found its stable thickness or its inner and outer edges. The composition is varied in a way Saturn's pre-existing rings were not. Those rings were the product of a single icy moon that disintegrated, primarily water ice, with some rocky contamination. This new ring contains the geological and biological history of an entire world. In the first 1,000 years, the ring evolves rapidly by ring standards. Particles collide gently and continuously, each collision damping relative velocities slightly. The cloud flattens into the equatorial plane that Saturn's gravity prefers. The orbital altitude of the ring stabilizes around whatever distance the approach geometry determined for each class of material. The ring develops inner and outer edges as the distribution of velocity settles. In the first million years, a lightest molecular components, nitrogen from Earth's atmosphere, water vapor from the upper ocean, light organic molecules from the biosphere, have been swept away by Saturn's magnetosphere, which imparts enough energy to these light species to allow them to escape the ring system. What remains is heavier: ice, silicate minerals, iron compounds. The ring's composition shifts toward what Saturn's pre-existing rings looked like: ice-dominated, with rocky contamination. In the first 10 million years, the ring has evolved into something that, viewed from a distance, resembles Saturn's existing ring system before Earth arrived. A thin, flat disk, pale against the black, following the equatorial plane. An observer familiar with the pre-collision ring system would notice differences: higher silicate content, a different average reflectivity, perhaps a different color in certain wavelengths. An observer seeing Saturn for the first time would see rings. In the next 100 to 200 million years, ring rain draws the material steadily inward. Ring particles drift towards Saturn at a rate determined by the interaction of their electrical charge with Saturn's magnetic field, and by small radiation pressure effects. The ring grows thinner over time, losing mass faster than any source replenishes it. The outer edge dissolves. The inner edge, where particles complete orbits fastest and spiral inward most quickly, feeds Saturn's equatorial atmosphere continuously. At approximately 200 million years after the collision, the ring that was Earth is gone. The material that was Earth's crust, Earth's ocean, Earth's atmosphere, the accumulated geology and biology of 4.5 billion years of one world's history, has fallen into Saturn's equatorial atmosphere. It is mixed into the chemistry of Saturn's cloud layers: the carbon, the silicon, the iron, the oxygen, the nitrogen, all of it dispersed into a planet that contains now more than it contained before, without knowing what it received. Saturn's cloud tops absorb the last ring particles. The orbit that Earth's debris occupied is empty. Saturn continues its 44 millionth plus orbit of the Sun. The rings are over. We have spent this time with a question the solar system does not have to answer. The physics is real. The Roche limit is real. The metallic hydrogen in Saturn's interior is real. The hexagon at Saturn's North Pole is turning at this moment. Enceladus is erupting. The rings, the ones that actually exist, the rings of an unknown moon that disintegrated somewhere between 10 and 100 million years ago, are falling slowly into Saturn's atmosphere at thousands of kilograms per second. These things are happening right now, without us directing them, without anyone watching most of them. And the carbon in you is real. It was made in a star that died before the sun ignited. It drifted through cold molecular clouds. It was incorporated into Earth's early chemistry and has been cycling through life on this planet for 4 billion years. Whatever rearrangement the universe makes of it next, it will continue. It does not require this particular configuration, this body, this moment, this breath to remain carbon. But it is this configuration tonight, in this moment, which is the only moment it has ever actually occupied, as is true of every moment before it and every moment that follows. The solar system is stable. Earth is where it has been for 4.5 billion years. Saturn is 1.2 billion kilometers away, drifting through its orbit, its rings catching the distant light, Enceladus erupting quietly into the E-ring, the hexagonal storm at the North Pole turning as it has turned since before we were here to name it. If your eyes feel heavy, let them close. The universe is holding everything where it is. If this felt like home, leave a comment when you wake up. If you're still here, the next chapter is waiting. The universe will still be here when you wake up. So will we. Good night.